Thanks so much, Jay. Thanks. Pleasure to be here as well. I wasn't really sure, knowing that the Grantham Institute is about climate, how focused I should be on climate and how much I should put in about geochemistry. And seeing the audience here, it's probably good that I've got a little bit of both of those in the talk. And the title gives away the fact that I'm going to try and squeeze some chemistry into a talk which is primarily about climate change. So let me start with a figure which hopefully is familiar to everyone in the room. This is from the latest IPCC report. And perhaps I made a slightly controversial remark at the top here, which is that global temperature is, relatively speaking, easy to predict. We've known for quite a long time roughly how sensitive the climate system is. If you increase the amount of CO2 in the atmosphere, roughly what that does to the temperature of the whole planet. You can do it from energy balance models quite easily. And you see here in this prediction for 2100 that for two different emission scenarios here, so two different amounts of CO2 in the atmosphere, the models cluster reasonably tightly in each case in terms of being able to predict the average temperature of the planet by the end of the century. Now, if you look at a figure like this, 4 degrees of rise is the sort of worst case scenario in IPCC here. And 4 degrees, if you ask most people on the street about what 4 degrees means, they think, well, not much really. It's 20 degrees today. It's going to be 13 on Friday, if we believe the forecast. So 4 degrees doesn't seem like a very big difference to most people. And in fact, 4 degrees probably isn't very much of a difference to most societies. The global temperature itself isn't really the thing that we care about most. And it's not the thing that people care about most in society either. So I think it's in some ways slightly unfortunate that we often use this metric to really work out whether global change, climate warming is going to be a serious issue or not. If we think about what some of the major issues might be, and I'm going to use this figure to introduce that, I've got sort of 3 that I'm going to talk about at least briefly today. I've chosen this figure because it shows the bit of the Earth that we live on. We don't live in the ocean, we live on the land, and it's a land-dominated view. And it also shows you, well, what I might pick on as 3 of the biggest implications of that temperature rise. And these implications are what actually are more important for societies. One of them is sea level. You can see the edge of the continent here. That warming is going to drive sea level change. It's already driving sea level change. And that sea level change is significantly going to impact cities and coastal development in the future. That's an unstoppable train of climate change, I think. Another issue is not global temperature, but regional temperatures, and particularly in areas where ecosystems are quite sensitive. And as an example that I'll talk about here, the permafrosted region in the Arctic, where we see exaggeration of temperature rise already in climate change, and we expect it in the future. And that's going to cause quite significant changes in here above what you'd expect for just the global average temperature change. And the third significant change that's really going to make a difference to societies is aridity and rainfall. And you see on a map like this how we see major changes in vegetation between desert regions and vegetated regions. And as those rainfall belts move because of climate change, that's also going to have huge human impacts. So those, I think, are three of the big challenges for climate, not the mean annual temperature, but things like sea level, things like permafrost melting, and things like rainfall change. Now, the problem with those sorts of implications is they're quite difficult to understand and to predict for the future. We haven't lived through these sorts of changes in the instrumental record. So if we want to understand them, we've either got to build a computer model that we think mimics all of the processes that are important for, say, sea level, and then we can run that forward into the future and see what happens. Or we have to be able to understand what happened in the world a long time ago in the past before our instrumental records. So we can use the world's history as our archive of climate change and climate process. Now, both of these have distinct advantages. If you build a model, then you can do exactly what you want with it, and you can make it do exactly what you think the emission scenario is going to be and where you're going to get to, and you can use it to do quite refined experiments. But the model might be wrong. You might just have processes that are missing in that model. Sea level might be driven by processes that you can't accurately predict at the moment. If you look back into the past, the problem is that there is no direct analogy for where we're heading. There's no point in the past where you can say that is the best analogy for the future. So what we have to do instead is to pick different periods which give us some process understanding of the climate system. But what we do know is that when we look into the past, that's telling us what really happened and what the world is really possible of undergoing. So I think the modelling and the paleoclimate are extremely complementary approaches, and that one of the slight failures in climate science sometimes is the inability of those two fields to talk to each other quite as much as they should do. Although I think we're seeing positive change in that sense more recently. So if people who don't look at paleoclimate archives, of which I suspect there are some in the audience, I'm picking on 4 of the most regularly used archives that we use to look back into the past here. Marine sediments, corals, ice, and stalagmites. If I just add another box to the bottom of these are positioned roughly in terms of how many years we've been working on these sorts of things. So the very first paleoclimate was really done, this continuous time series of paleoclimate was done in the 1950s using marine sediments with people like Urey and Miliani working on some of this early stuff. Corals really came into the fore in the late 60s and during the 70s as another archive that we can interrogate to try and understand how climate has changed. Ice cores became dominant in the 1980s, papers by Berner and Barnola that really, in my view, initiated our current concern about CO2 driving change. It was these ice core records that first showed us that carbon dioxide beat in time with global climate change during the ice ages and first started making us really believe that carbon was what pushed the Earth's climate around. So the ice core is extremely important in our development of understanding of climate change. So you can see that compared to those other 3 archives, stalagmites, which I'm going to focus on today, are a relatively young archive. These have not been worked on quite so much as other things. I've picked on the 1990s, reflecting Bar Matthews' early work, but actually Larry Edwards and the Minnesota crowd really set this alight in the noughties, so a bit later than this. So you can see that stalagmites are a rather less explored archive than some of the other paleoclimate ones that we look at. But they are really fundamental because we get stalagmites in situations where we live. We get them right in the middle of the continents. If I flick back to that continental image of a minute ago, you can get them in those settings where the people live and where we really need to know about how climate changes. So for those people who don't think about caves and stalagmites, let me just introduce this environment and what we need to get stalagmite growth. So I'll just talk you through what happens. It rains on the surface. The rain makes vegetation. The vegetation rots, releasing carbon dioxide into the soil. That carbon dioxide makes carbonic acid, which, as the name suggests, dissolves the limestone in a limestone terrain. And that limestone then percolates down into the cave. When it gets into the cave, the system effectively reverses. The CO2 that was high in the soil because of plant rotting is released to the cave air, and as it's released to the cave air, that causes reprecipitation of the limestone that you dissolved. So it's not an evaporative process. This is a CO2 uptake and degassing that causes our stalagmites to grow in caves. If we summarize that and think about what is actually required to make stalagmites, there are 3 things that we need. We need water to drip into the caves. It needs to rain and percolate into the cave. We need limestone to be dissolved and reprecipitated, and we need air for the CO2 to degas into. So if we have these if we have these 3 things, we're going to grow stalagmites. And what I'm going to do for the rest of this talk is to show you how we can use those stalagmites to try and understand paleoclimate in the past and understand the processes that push climate change, the changing climate to occur. So pretty pictures of stalagmites. One of the things that we know about these, this is a nice example because it's from the type locality Karst in Slovenia. You see these wonderful examples of stalagmites here. And we know that these can grow for up to hundreds of thousands of years. So they're growing and capturing a very long chunk of Earth history for us. How do we know that they grow for this long? Well, that's really one of the huge benefits of working on stalagmites, is that we can date them extremely precisely. And of all the paleoclimate records that we look at, these are probably the best dated archives that we have. What we use to date them are these isotopes called the uranium and thorium series nuclides. On a chart of the nuclides here, protons against neutrons, there are 3 isotopes, 2 of uranium, 1 of thorium, which are very long-lived. They're radioactive, but they're very long-lived. So they've been around on the Earth since it formed, and they are gradually, very slowly decaying to make a series of other nuclides. But because those nuclides that they make, there are the same 3 isotopes, let's just follow the 238 uranium here, because the nuclides that they make are themselves unstable with a short half-life, we get this whole long series of decay products from each one of these isotopes. Now these things are an absolute bonanza for the geochemist. And that's what I am really. I'm not really a climate scientist, I'm a geochemist. And what these things are basically tools for the geochemist to understand rate and timing of events in the past and in the modern. So we're going to use some of these, and I use these in all different sort of contexts, use them a lot in the ocean as well, but here I'm going to be showing you how we can use these to date stalagmites. And the isotopes that we pick on in particular are these two here, uranium isotope, which is very soluble, and therefore there's lots of it in water, and a thorium isotope, which is very insoluble, and therefore there's none of it in water. And that means that when you grow a stalagmite, or a coral, or anything made of carbonate, you capture a ratio, you capture basically a thorium to uranium ratio of 0. No thorium, but lots of uranium. And that's shown in this graph here. So with, when you capture the carbonates, in this case a coral perhaps, you start off with a thorium to uranium ratio which is very low, and if that's then locked up in the sample, in the stalagmite or the coral, it gradually decays towards this magical value of 1. So we can use this systematic change, because of radioactive decay, to give us very precise ages for carbonates such as stalagmites. But you'll notice that this archive, this chronometer rather, runs out at about 400,000 years. We can only go back to something close to 500,000 years before we run out of steam. So we can use this to date our stalagmites, and that's going to be a key to the science that I'll tell you about. We do this dating in a clean lab. You have similar labs quite close by. Here your new ones look really rather similar to the Oxford ones. This is an example of one of the Oxford labs here. And then having processed the stalagmite, taken out the uranium and thorium that you want to measure, we take them to a mass spectrometer. And again, this is a rather similar instrument to some of those which are hosted here in Imperial. And we can measure the uranium and thorium very precisely on these sorts of instruments to generate time series. I'm not sure you'll better read the ages on here, but this is this lovely stalagmite sample from the edge of the Sahara in Morocco. You can see how we can date it with a young age at the top, much older ages at the bottom, and we can date the different phases of growth of this sample as you go back through the last 500,000 years here. So this chronology alone is able to tell us a lot about climate, and that's what I'm going to focus on actually for quite a lot of the talk, is just using the chronology to learn something about how the climate system works. We're working in a lot of different places here, and don't worry, I'm not going to try and go through all of these, but just to give you a sense that we can use stalagmites in very many different settings. I'll return to this figure to sort of guide us through the talk. And so it's worth introducing that the base map here that I'm showing you is rainfall. So the colours on here are July rainfall, demonstrating something about the climate system and which bits of it we're working in. So this is an example of how chronology alone can help us to understand climate. Let's look at the example of sea level, one of the three big climate things that I was concerned about earlier. And I'm going to pick on Bermuda here and show you a rather nice picture of a cave here. These are stalactites under air. This black sheet here is sea level. This is a cave that's today submerged, very low tidal range, so it pretty much sits exactly there. You can see the reflection of stalactites, but you can also see under the seawater here rather nice stalagmite, and then quite a lot of other smaller stalagmites here. And if you think about what we need to grow stalagmites, you've got to have dripping water and you've got to have air for degassing. And these ones under here don't have either of those, so they're not forming today. These stalagmites don't form today, and therefore they tell us that at some point in the past, this sea level must have been down below the level of those samples. So if we simply go to those samples and measure the ages at which they grew, we can work out something about the history of sea level. We can work out when it was lower than today. Here are some examples of samples that we're just starting to get going on in Bermuda to try and understand this problem. This one here grew 20 metres below modern sea level, and you can see there's quite a noticeable hiatus where it stopped growing here, with these circlid worms that grew on the outside of it when sea level must have flooded the cave. So this is showing you a period where sea level was at least 20 metres lower than today, and then it came up and caused these worms, and then it went down again to form this bit up here. So we can get a very accurate picture of when sea level was at different levels from this sample. And here's an example that's taken from above modern sea level, about 2 metres above the current height. Again, you can see a clear hiatus in this cross-section through a sample here. And we think that probably formed at the last interglacial when sea level was some 7 or 8 metres higher than today. So that, I hope, gives you a flavour of how chronology alone helps us to learn something about climate change, in this case sea level. This is work that we're only really getting going on, so I'm not going to focus on this. But it helps you to understand what's coming up next, which is to think about Siberian permafrost, to think about the history of permafrost through time and how responsive permafrost is to climate change. So we're going to look at a series of caves next in this area here. I've been doing a lot of chemistry here, so let's get back to some climate for a minute. Let's look at a figure of global mean annual temperature. Sorry, not global. Mean annual temperature for a map of the planet. And you can see that in the blue colours on here, there are significant areas of the planet where the mean annual temperature is significantly below zero. So the dark blue that I pointed to is about 10 degrees below zero. So these are areas where, although in the summer you may get the upper part of the soil melting, because of diffusion of heat down into the soil, at some depth of only a couple of metres, the ground is permanently frozen. It doesn't melt in the summer, it stays frozen because the mean annual temperature is below zero. Why should we care about these sorts of regions that are going to have that frozen ground, this permafrost? Well, first of all, a definition. Permafrost is ground that remains frozen throughout the year, and it will melt when climate warms, if it warms enough. Why should we care? Northern Hemisphere permafrost contains about 1,700 gigatons of carbon, so it's more than twice that in the atmosphere, and we expect that will be released during warming, and the rate of that release and the magnitude is obviously important to constrain. That thawing will also cause large ecosystem change, which is important for the natural world. It's actually quite important for societal change as well. If you think about Russia, clearly a major geopolitical influence at the moment, and they're going to find a much better ability to grow arable crops in the future, because vast areas that are permafrosted today are going to be much better farmland in the future, at some point in the future. And indeed, it's not only farming, it's infrastructure, so roads, railways, oil production is built on permafrost and relies on that material. So we really would like to know what happens, what will happen to permafrost as we go forwards into a warmer world. But as a society, we've never seen permafrost change before. It's been there. How is it going to change? What feedbacks are in the system? How do we expect it to respond at high latitudes to the mean annual temperature that we find so easy to predict? Now, this is where we can. This is an example of where we can use stalagmites and paleoclimate. First of all, I'm going to show you this map, which demonstrates the extent of permafrost. It's kind of a weird projection, isn't it? But there we've got the Southeast Asia. There's India. There's the Tibetan Plateau, and you can see that these dark blue areas on here are areas where the ground is permanently frozen. This is the permafrosted area. We want to know how rapidly that is going to melt as we go into the future in a warmed world. So this is work that I should make sure I mention my collaborators on. And this work, in fact, was led by Anton Vax, who's recently moved back to Israel, with Seb Breitenbach, and then with several local cavers and scientists from the Russian region. What we want to do then is go to caves, and here's us in front of one of those caves, and see where we get stalagmites. Let's think about those 3 criteria again. You need to get drip water into the cave if you're going to make stalagmites. So if the ground is completely frozen, any water that tries to go into the cave is going to freeze in the ground, become solid, and not get into the cave. So if you see the presence of stalagmites in a cave, it cannot have been permafrosted. The water must have been able to go through the soil and into the cave. So it's another example where just by dating the samples, we can work out the history of permafrost and see how that corresponds to changing global climate conditions. So we're going to go to that cave. This is on the way up there. One of the aspects of doing stalagmite work is the fieldwork component. This is us trying to cut away through turn a footpath basically into a road, so we can get far enough north to find caves that are in permafrost today. We meet occasional obstacles like this river. One of the great things about Russian drivers out there is they don't seem to care. He just carried on straight. There's the road the other side. This is our road on our side, and this is us in the middle of the river. He barely blinked. He just kept going, and I was quite shocked when he did this, but it seemed to work out. So we got there, we got to the first of the caves that I'll show you a picture of. This is inside a cave called a Hodnitskaya, a hunter's cave. And this is exactly at 0 degrees today. Caves average the mean annual temperature for you because they're deep and they kind of get rid of that seasonality. And the cave temperature inside a Hodnitskaya is 0 degrees. And therefore it's poised right at the edge of the permafrost belt today. Here's a nice example of ice crystals forming on the roof of that cave where you have cold and warm air mixing together at the mouth of the cave and freezing atmospheric moisture onto the surface of the cave. Although it's at 0 degrees, we find that the cave is richly decorated. There's lots of stalagmites inside it. So these have grown at times when enough water is getting into the cave to cause significant growth, which is just about happening today. Just about get a little bit percolating in today to cause this growth. So we take some samples. We're quite careful not to protect the environment and cause minimal damage while we're doing it. We take samples, take them back to the lab, and we do some chronology on them. This is the same sort of uranium-thorium data I was talking about before. And we can learn from this example here, for instance, that there must have been thawing at particular times in the past, with presumably the gaps between these intervals representing times where the permafrost was quite strong. So that's a cave poised right at the 0 degree isotherm. And we can go a bit further north. So that was this cave here, Hodnitskaya, on the shores of Lake Baikal. We can go north to Botovskaya, plenty of growth still there, and we can date that. And we can go further north still to Lenskaya. This is really now into a strongly permafrosted region up in this far north. To get there is tricky. You have to wait to the right time of year and you have to drive up the side of the river. There's no roads going that way, so you either entrust your life to a Russian helicopter, which I've not been willing to do so far, or you drive along the edge of the ice to get up into the far north. When we get to that far northerly cave, we still see growth, much less than before, but even though we're right in the heart of the permafrost region now, we still see evidence of there being periods of thawing in the past. And if we date the samples here, on these couple of sample pits here, give us an age of about 400,000 years, and that's the most recent material we can find from this cave, suggesting that this cave has been completely frozen, permafrosted for nearly 500,000 years. These other pits that you see on this sample, we can't date with uranium-thorium. It's run out of steam. It's got to its 500,000 year limit. So if I summarise our chronology for all these samples, then you can see it on this figure here. There's quite a lot of data here, but let's just focus on the top panel. These are the three caves, the Hodnitskaya, Botovskaya, Lenskaya, plotted against age, with the points on here representing our uranium-thorium ages. And then this is the closest thing that we have in a paleoclimate record to mean annual temperature. This is the temperature of the Pacific warm pool, reconstructed using magnesium calcium, and the warm pool is pretty close to mean annual temperature. So, or at least its changes in that, are pretty close to changes in mean annual temperature. So you can see the history of tropical temperature here, and you can see that whenever it's as warm as it is today, plotted by the red line across here, we see stalagmite growth in the two southerly caves. This is showing us that whenever the temperature gets a little bit colder, permafrost is extending much further south past these two caves, and we're not seeing any growth at all. But it's also showing us that even when we get a little bit warmer than today, we're still not pushing the boundary of permafrost up to the far northerly cave here. And it's only when we go back to this period of really extreme warmth, about 400,000 years ago, where temperatures were about 1.5 degrees warmer than today, that we start to see some growth in the far northerly cave. Just by visiting those three caves and dating them with uranium-thorium, we've got some history here about how sensitive permafrost is to tropical temperatures. Now, I wouldn't ever let a student get away with contouring a map with only 3 points on it, but here we go anyway. Here's a map with 3 points on it, and I've drawn some rather speculative contours through this map. But it's suggesting that with warming of a little bit, maybe a degree, we might cause a bit of permafrost melting, but we're not really eating away into the really deeply frozen material. But with 1.5 degrees, we're starting to push the permafrost boundary much further back. We've got another cave that's further north here, which doesn't get any growth at all in the last 4 million years, and but that's work in progress. It's compared to today, this value. So that's a good 0.7 of a degree to play with there. So, So this is as far as we can go with uranium-thorium, that chronometer that I showed you at the beginning. I said that runs out of steam at about 400,000 years. But we'd really like to be able to look back further into the past. And this is work we've been trying to do more recently. These uranium isotopes, when they eventually go through their whole series of intermediate isotopes, end up as lead isotopes, shown on the bottom over here. And uranium-lead doesn't ever run out of steam. These are stable isotopes, so they just stay there. And we can use the uranium to lead ratio, in theory, to date things that are much older. In fact, these are quite difficult chronometers to use on very young stuff. And that's been our challenge from a geochemical point of view, is working out how to use uranium to lead to give us ages on what are relatively young samples. But that's something we've been able to do. We've worked out techniques to separate uranium and lead from stalagmite samples, and then been able to push back the chronology that I showed you before for uranium-thorium right back into the uranium-lead era. So this is the same sample as before from that far northerly cave, Lenskaya. We couldn't date this with uranium-thorium. Now we can with uranium-lead, and you can see that the pits give ages that are broadly getting older as you go into the sample, and telling us when there were periods of permafrost collapse in the past. This is a summary. This is unpublished work from Anton Bax and Andrew Mason and others, and it's showing, again, with the tropical warm pool temperature in the middle here, but now for a much longer period, the last 1.5 million years, compared to periods of growth of stalagmites, and therefore periods where the permafrost had thawed. Now, in general, you still see the same pattern, that whenever the temperature is significantly above modern, you're getting some growth. But we're now seeing growth in some periods which are only just above the modern value, and certainly cooler than the last interglacial. So it's clear from this older work that the history of permafrost is not quite as simple as just a 1.5 degree warming causes melting. And there are other aspects of the climate system that feed into the melting. So when we go back a long way into the past, back more than 1 million years, the system is thawed even at temperatures in the warm pool of rather less than today. And that's something we're currently thinking about. So I've kind of done sea level very briefly, didn't tell you anything useful, but told you how stalagmites might work. I've shown you a little bit of our work on permafrost, about how we might try and learn about the sensitivity of permafrost to climate from stalagmites. And let me just wrap that up before I move on. Some of the summaries here. There's plenty of speleothem in Siberia, so there must have been periods when it was thawed. And this forms only in conditions as warm as today. And that means the permafrost extent must have been much larger than today, even with climate a little bit colder. It's quite a sensitive boundary. Tropical temperature rise of about 1.5 degrees is enough to cause significant reduction in the area of permafrost and release of carbon dioxide. And from a paleoclimate point of view, that means that the permafrost is acting like a carbon capacitor. During the glacial periods when it's cold, it's storing up carbon for us over a much larger area. And then during the interglacials, when it starts to melt, it's pumping that back out into the atmosphere and maybe helping to contribute to the glacial interglacial CO2 changes. But it's the rapid thawing that we're undergoing at the moment due to global warming which is going to cause a more rapid release of that carbon dioxide, and the stalagmites are giving us a clue about just how rapid that might be and how sensitive that might be. Okay, so I don't want to talk about chronology the whole time. Let me think about the other axis, the y-axis. So I've shown you that we can get useful information by dating samples, and so far that's all we've done. But what we really want to do is be able to get time series of climate in the past and understand how things changed through continuous periods of time. Now, on this figure, you can see how powerful that is from an ice core. This lower figure here is an ice core record, showing that we can get a lot of data about temperature variability and abrupt climate change from measuring, in this case, stable isotopes of oxygen in an ice core. And this is one of the very first influential stalagmite papers in 2001, showing that somewhat similar patterns of climate change were observed in oxygen isotopes in a stalagmite. This one is from the middle of China, from a Monsoon, China region. So why might oxygen isotopes be telling us something useful about climate? Why might they respond to climate change? Let's just think about the basics of oxygen isotopes in a cloud. So if you imagine a cloud that's got a coexisting liquid so raindrops and vapour. There are 3 different isotopes of oxygen, and the heavier of those go preferentially into the liquid. So the oxygen 18, for instance, goes into the liquid, which is why it's a higher number, a heavier number on here compared to the vapour. So if that liquid falls out of your cloud, the residual water in the cloud must track to progressively lighter and lighter isotopic composition. So basically, the more it rains, towards the right of the figure here, the lighter the isotopes should become. And there are both the isotopes in the cloud and in the rain that falls out of it. And that's what this figure is showing. Now, of course, what makes the atmosphere rain, what makes a cloud lose moisture is temperature. So as you cool the cloud, either through moving it to higher latitude or by moving it up in the atmosphere and cool it, that's going to drive this progression towards progressively lighter isotopes. So I'm going to stay in Siberia for a minute and show you how this works. This is from the same setting that we looked at before from this permafrosted region. We've got air temperature versus Delo-18 in rain, or in rivers in some cases. Several different data sets here, and you can see that there's really quite a nice relationship. This looks quite promising, doesn't it? It means we should better use Delo-18, this isotope value, and get at temperature, which would be quite a nice thing to do. Then we can turn that record I showed you into something really climate-related. If we do that for our Siberian sample, here's 10,000 years worth of oxygen isotope data. This is the Holocene period here. And what you see here is, sorry, I didn't point this out, first of all, I should have done. This relationship here tells us the sensitivity of this proxy to temperature, about 0.15 per mil per degree C. If you look at our actual record for Siberia, we see changes that are enormous. These changes in Delo-18 suggest that we've got 20 degrees of temperature change at this setting, and that for significant periods of the growth, it was below 0. And clearly, you can't grow a stalagmite if it's below 0. So these Delo-18 numbers are not recording temperature in any simple way. And this is the curse of stalagmites. The Delo-18 is extremely difficult to understand. And here, it's not just being caused by temperature change. It's being caused by the source of the water and where the water's come from. So if you take water all the way from the Atlantic in the westerlies, it's had a very different trajectory than if you bring it up through the monsoon system into Siberia. And that makes understanding these sorts of records rather challenging. But we have to try and do that, because that's what we want to get is time series. We're still working on the Siberian record, so the thing I'm going to finish off with instead is to talk a little bit about the East Asian monsoon, where we've had some more success at understanding another proxy or other proxies to try and get at time series of climate. This is where this base map is useful, because if we're thinking about monsoonal rain, you can see that very clearly in the July rainfall pattern here. So you've got the intertropical convergence zone across the whole globe pretty much, but then spread out, smeared out into the northern hemisphere because of the heating of this land mass during northern hemisphere summer. And you can see just how important that is for rainfall patterns. And something like a third of the world's population live in this region, and the primary weather signal they see is monsoon changes because of that pattern. So we'd really like to be able to understand what's going to happen to this, how is it going to change into the future. That's actually something that's rather difficult to get at from models. And this is an example from the latest IPCC report. For those who haven't looked at these reports before, this sort of hashing on here means that the change is not taking us outside today's natural variability. And the stippling means that the models, most of the 39 models run here, agree with each other about the change that's going to happen. So if you look in the region of the monsoon highlighted here, you can see that it's outside of normal variability, and we're predicting changes of something like 20 to 30% in terms of rainfall. But there's very little stippling, very little confidence about what's actually going to happen to monsoon rain as we go forward into the future. So models, although agree about the sense broadly, they don't agree completely about either the sense or particularly the magnitude. So we'd like to understand more about the monsoon by looking into the past. I'm going to pick on one particular aspect of this, although I think that the monsoon is an area where stalagmites have been particularly important for understanding climate change. But I'm going to pick on this pattern that you see in today's climate and is predicted to continue into the future. In the North Atlantic today, we see pretty much zero temperature change. This is the last, 100 years worth of change. The whole world's gone red, it's got warmer, except for this little patch up here, which really hasn't warmed very much at all. And we know why that is, at least we think we know, and that's because there's a systematic change in the way that the ocean circulates, which is progressively changing the amount of heat pumped into the North Atlantic region. So today, the ocean circulation, you get deep water forming in the North Atlantic, going into the deep ocean and drawing the warm waters from the tropics and the mid-latitudes up into the high latitudes. And it's that heat release that helps to keep us and Greenland quite warm today. And this whole overturning limb here is getting weaker in the last few decades and is projected to continue to weaken into the future. And that's what's causing this relative cooling here, is it really pumping less heat northwards. So what's that going to do to the monsoon? It's a long way away from the monsoon, but we've got a big perturbation in temperature in the northern hemisphere. Northern hemisphere is also where the Indian and Southeast Asian monsoon is. Is there a linkage between these two bits of the climate system, really some distance apart? And what do we expect that linkage to look like into the future? Well, we can look back in the past to see what the linkage might be. This is an ice core record. This is from Greenland. Perhaps it's kind of up here somewhere. So it's going to tell us about temperature in this region. And you can see that the temperature's been broadly stable, but there's been this event here called, for fairly obvious reasons, the 8.2 kiloyear event, where temperatures got much colder. And you can see that this is three different ice cores stacked on top of each other. You can see it blown up. We have a pronounced event of about 150 years where we know climate was in the North Atlantic region was cold. We have some understanding of why that is, and it's to do with the change of that ocean circulation that we're also expecting in the future. So what happens at 8.2 thousand years ago in the monsoon? So let's go to a cave. Here's one of my favourite caves. We worked a lot on Hershang Cave here. It's in a tributary of the Yangtze. You can see it's not entirely easy to get to. It's a big cave. Those are people you can see in the entrance of it. And this is the path that we have to carry our samples out of when we take them. Again, I should acknowledge collaborators here, in particular Chao Yong-hu is the Chinese scientist who's really led this program, Yu Hui, who's a graduate student who worked in Oxford, and I'll be showing mostly her results. So it's a nice cave. It's quite pretty inside. It's got some enormous samples. Here's one that we've worked on a lot, HS4. Chao Yong's not a short man, so this is giving you an idea that this is really an enormous sample that we've been working on. And we can get lovely chronology on it. So if chronology was enough, we've got a lovely time series here of age versus distance. We get a nice record from this sample. You get a sense also from this sample of how difficult it was to get out. This is heavy, and we had to break it into bits and carry it down that path rather carefully. So in the monsoon, it's always raining. As we know, the monsoons always function to some extent. There's plenty of carbonate. There's nodes of limestone in China. And there's lots of caves with air in them. So you've got all the criteria to form stalagmites always. So just dating them isn't enough. You're not going to learn anything just by dating them. So we really need to have a y-axis here. But the y-axis is difficult. Delo 18 isn't a very easy to interpret proxy. So that's something that we've really been trying to understand in Oxford. One of the ways we've been trying to do that is to grow stalagmites in the lab. So we're kind of mimicking a soil, and then we're pumping that soil water and dripping it onto a glass plate in a mimic of a cave. This schematic shows you how we've got the Oxford cave set up in a lab. This is some of the top of that equipment with the cave effectively in the box below you here. And this is obviously not climate, right? This is chemistry. And for the geochemist, this is what really is some of the interesting science here. The thing that drives the question is a climate one. We're trying to understand how climate operates. But the interesting, challenging science is understanding the chemistry of these things, trying to get to the nitty-gritty of how do stalagmites form, why do they look the way they do, and how do they respond to environmental change so that we can use them in a useful way. Here's some of our homemade stalagmites. This is after 7 days of growth. So if we kept this going, we'd end up with a big sample, but this is just a little smear of carbonate on a slide here, and an SEM image showing you the nice little grains of carbonate we get. So we do this in the lab to try and understand things. We also do it in the cave. So in Hershang Cave, we're monitoring it very carefully to look at the temperature outside and inside the cave. We're looking at drip rate in the cave, how much the water comes into the cave. And again, we're putting these glass plates out to understand how the carbonate chemistry responds to the environment around us. When we do that, we can learn something about what the y-axis that we might use. An example that I'm going to pick on here is magnesium calcium. Simple thing to measure. We can measure it very easily in carbonates. We see that there's a temperature relationship here between magnesium calcium and temperature. But actually that relationship is very weak compared to another one. That red square's moved. Don't know why that's happened. The red and black square should be on top of each other. Sorry. What we see that compared to all the glass plate data in the lab and in the field, we see that the magnesium calcium ratio in our real stalagmites goes much, much higher than that. And that's happening because when we have slow drips in the cave, those drips sit on the top of the stalagmite for a long time, and they have a chance to do more growth of carbonate. And as they make more carbonate, they have to evolve to a higher magnesium calcium because they can no longer fuss about which element to take so much. They're just taking whatever's left in the water, and they're taking up more and more magnesium. So this high magnesium calcium values here are driven by dry conditions in the cave. We can effectively measure magnesium calcium and get a sense of how much it's raining in this setting. So let's do that. Here's a record, that nice chronology we saw before, last 9,000 years. Oxygen isotopes, because everyone has to measure that, because we always do. And then compared to magnesium calcium below on here, it's an inverted scale. So what you can see is that at 8.2 kiloyear event, we're seeing very high magnesium, and that means very dry conditions. A lot of precipitation on the surface and very dry conditions. And that fits with our understanding of oxygen as well. So magnesium calcium is showing us clearly that there is a rainfall response in the monsoon system to temperature change in the North Atlantic, which is happening thousands of kilometres away. We can see that from other proxies as well. This data was published a couple of years ago now, and we've been working on some other proxies since then. This is one from a graduate student in Oxford, Rob Owen, who's been looking at calcium isotopes. This is one for the isotope chemists in the group. And calcium isotopes have got several advantages in the fact they're much less prone to effects from other changes than magnesium calcium. And we can see again, coincident with the 8.2 event and that spike in magnesium calcium, we're also seeing a systematic change in calcium isotopes. Anyway, but let's go on and actually apply these proxies and look at the 8.2 record in detail. Here you see that enormous 2.5 metre long sample that you saw with Chaoyong standing next to it. Here's 4 centimetres from taken out of it with just the 8.2 kiloyear event in it. And you can see the lovely annual layers that we get in these sorts of samples. So we're going to really take this to pieces now. These are just range finding samples here. We're going to take this to pieces in a lot of detail and work out what happened at 8.2 kiloyears. This is the same sample again. Shows you the layer thickness, which we can count. It shows you the magnesium, calcium, and you can see the magnesium going way high. The highest values we see in the middle of this section here. And the oxygen goes to very isotopically heavy values, which again we think reflects less rainfall. I'm running short of time here, so I'm going to skip through these quite quickly, but we can date it very well and play some clever games with dating to make it even better. And when we do that, what we find is that we see a drying event in the East Asian monsoon, which is very similar in form and duration to the cooling that we see in Greenland. So this is the Greenland ice core showing you the cooling for 150 years, and this is the record of drying that we see in the stalagmite records. Really lockstep, one-to-one relationship. When it gets cold in the North Atlantic, the monsoon gets weaker. We see a clear teleconnection here in this data set, and indeed in some of the other published data sets for other Earth periods, between cooling in the north and weaker monsoon. What causes this is interesting. Some people have speculated that information was transmitted from the Atlantic into the monsoon region through the ocean. I don't think that can possibly be true. If you look at the phasing of these and the similarity in the records, you can't get a signal through the ocean all the way to the monsoon on that sort of temporal resolution. So we must be talking about some sort of atmospheric-dominated teleconnection, and the sorts of likely players are that you're changing the rainfall or the snow cover over northern Asia as a consequence of cooling over the Atlantic, and that increased rainfall or increased snow cover is then leading to later and weaker onset of the monsoon. Okay, so I've taken you through a bit of a whistle-stop tour here. I'm not going to deal with any more of these. What I've shown you is very briefly how we might use stalagmites to learn something about sea level, work we're just getting going on. I've shown you a little bit about how we've already used it to learn something about the history of permafrost and how permafrost is sensitive to tropical temperature and therefore global temperature. And I've also at the end shown you something how we can use stalagmites to learn about past rainfall and learn about how rainfall responds to climate change in other parts of the planet. So 3 examples of how we can use paleoclimate and chemistry in caves to learn something about the climate system. This is definitely not the end of the story for stalagmites. We've only started working on them quite recently as a community, and there is a hell of a lot more to learn. I've shown you already that uranium lead enables us to go way back into the past, so we can look at much older samples and think about how climate has changed on longer time scales. And these samples, as you might just about be able to see the annual layers in this sample as well, these samples are layered in such a way that we can measure them at monthly resolution. We can really start to think about doing paleo weather on some of these samples. And you can see some of the examples of chemical records from such samples showing clear seasonality. So we can actually start to get a sense of what happens in interannual variability and seasonal variability. And this is all territory to be explored in the coming years with stalagmites. So I'll shut up there and take any questions that you have. Thank you. Yeah, it's a good question. I mean, certainly a fair bit of the methane that's in the the carbon that's in the methane is there as the carbon that's in the permafrost is there as methane. And as the permafrost melts, that will be released. The question is how quickly it will oxidize, because it may oxidize quite quickly on release, and that's something that people are looking at with field experiments. We're also just starting to try and understand that from a cave perspective, but I think the field experiments will tell us how much of it gets oxidized from methane into CO2.
So the teleconnection that you mentioned towards the end,
Yeah.
if it is indeed an atmospheric effect, then it should be noticeable on the time scale. So I'm wondering, is it something that has been suggested present day, observations, for example? Is there an interest in?
Yeah, I'm pretty sure I haven't got that slide. You can see a relationship, but it's not very strong. If you look at interannual, take a bunch of climate data in the North Atlantic, interannual summer temperatures, and compare that to monsoon strength in Asia, there is a link, but it's obviously there's lots of other things that drive that interannual variability, and it's not a particularly statistically convincing link. It goes the right way.
Take the snow over ratio, it's there, but it's not that strong between the monsoon and the amount of snow.
Yeah. Yeah, exactly. So you can see there's sort of a bit of a hint, I suppose, but it's not really the smoking gun that you need from the modern data. The paleo data is showing you that if you change the sort of mean state, shift the whole system, then you're seeing a response.
You see on one of the slides, the rapid increase in temperature causes a significant release of carbon from the permafrost. What would you call significant?
Well, there's 1,700 gigatons of carbon in the permafrost. So if you were to melt back a third of that or something, then it's getting on for 1 atmosphere's worth of carbon. If you do that slowly, the ocean will absorb it for you. But if you do it very quickly, which we may do if we warm the world enough, then a large amount of it will stay in the atmosphere. And it will become a significant positive feedback on our own carbon emissions. Is that enough of an answer? I mean, do you want to come back to me if you want? What we don't know from this data yet is just how quickly, if you had a step change of temperature, bang, how quickly would that cause the permafrost to melt? And that's something I think we actually may be able to get at from stalagmites by looking at C14 in some of them. We don't know that yet, but it won't be that long. It will be decades rather than centuries for the heat to diffuse down and start to cause collapse.
temperature changes and not changes in the local, like, water stream, so the change in the water stream. Do you have any idea how to say what the changes came from, or?
Well, it can't, if the region is permafrosted, so if the ground is frozen, you cannot get water into the cave. And if you go into any caves in the far north, there's no water dripping in them today. And it's just, you can't, if you start, even if you have water in the surface in the summer, if it starts to percolate down into the soil, it gets to a layer where the soil is below zero, and then it'll freeze. So it has to be a temperature control. You have to relax that temperature constraint before the water can get down into the cave. Perhaps it's worth saying that caves are recharged from above. They sometimes have rivers in the base, but they don't grow stalagmites. The stalagmites that we find are formed by drips falling through the soil and the overlying rock into the cave. And if that's frozen, you can't do it.
I guess it's really interesting long record of ski events through the journey. With it, we have it's potentially going through carbon cycle. Do you see how this can fit into things like the mid-Pleistocene transition or any of these other climate changes over about 1.5 million years?
I think I'd put it the other way around, actually. Although two and a bit atmospheres worth of carbon is really important for us if we can release it quickly. That will make a big difference. On very long time scales, if you release that into the atmosphere, but then you can mix it into the ocean, it doesn't make a very big difference. Remember, there's something like 60 times more carbon in the ocean than there is in the atmosphere. So another 2 lots from permafrost isn't quite so important on long time scales. But I think that I'd actually turn your question around a bit and say the mid-Pleistocene transition seems to be a place where climate started to function differently, and we might be seeing that reflected in the permafrost records. The ones I showed you here went back to about 1.4 million years. We actually have some that go further back still, which we're still working on. So I think we're going to try and understand how long-term global change, such as the mid-Pleistocene transition, will cause, or has caused the permafrost to behave differently. That is true, and that's exactly what the last question was picking up on, actually. So, no, that's absolutely fine. It's good to explain it. Let me find the relevant record, which is this one, right? So, people argue about exactly how many of them there are, but there's something like 800,000 year cycles in the last 800,000 years, which you can count back. Prior to about 800,000 years, the climate system is dominated by 40,000 year cyclicity. So this is a switch in the climate system between one of the Milankovitch frequencies and another one, and it's termed the mid-Pleistocene transition. We don't really understand why. This is one of the problems. There are models to explain it, but none of them are really proven or disproven. So that might be, it's tantalizing that the 800,000 year number here corresponds to what seems to be a significantly greater chance of getting stalagmite growth. So maybe in the pre-mid-Pleistocene transition world, we were seeing a generally warmer northern hemisphere.
I just can't resist picking up there. When you look at your green curve at the bottom of the probability, it doesn't quite look like what we probably expect from a lot of climate records for that time interval. So the intervals where we know it gets really warm, like stage 11 or stage 31, and you collapse probably Western Africa, or whatever you want to think about, they look a bit like non-events compared to some of the other things you see out there.
No, it's tantalizing, isn't it? And some of this is presumably sampling noise, because what you're doing is taking as many stalagmite samples as you can and dating them. And it might be that if we had 10 times more, then the peaks would change their relative magnitude. But at least we're getting some growth in 11 and 31. It's just what's striking is that we see so much more growth in some other interglacials that are not thought to be quite so warm. Well, this is the data, and you have to try and interpret it, and that's what makes it fascinating.